Okay.
Okay. So good afternoon, everyone. We're in the second unit of Operators Without Border, the Distribution 1-2 refresher. So hopefully you can all see the PowerPoint. Feel free, if you have any questions, to shoot them through chat, and I can try and answer them. With my advanced years, sometimes I don't notice the chat right away, but I will keep an eye out for it and try and respond. Multitasking is getting harder and harder for me, I find. So,
Yeah.
But without further ado, what we're going to do is talk a little bit about, well, I put review math assignment, but I'm going to put the answers out there afterwards. And then we can go through them probably the next week or two, because I don't want to take up the whole time with that. Because you do have access to the PowerPoint, and if that's not good enough to work through, what I was telling Ignatius, I think what we'll do is we'll do a session on math and hydraulic review, disinfection, and so on, as opposed to putting out new info. So hopefully that works. But what we're going to talk about today, and keep in mind, what I'd like you to do while we're going through this is think about your own water system, the systems you work with, the system that, you know, in the community that you live, because you're going to see how a water system works. So all of the details that follow, types of pipe, types of water meters, hydrants, pumps, all that wouldn't be worth a hill of beans if we weren't able to pressurize the water system. And then, of course, we're going to talk a little bit about that in terms of static and dynamic head, how we calculate flows, not just the math formulas that we did last week, but how it actually works in a water system. So that when you're out working in your distribution system and you read a pressure gauge and you see a number, so many kPa, you'll actually be able, and this is what I've always told operators here, is I want you to try and visualize how high that column of water is above your head. Because when you look around your surroundings, and if you think, okay, I've got 20 or 30 meters of head above the fire hydrant or above my pressure gauge, I can actually visualize how much energy is available in the system with or without the aid of pumps or reservoirs. And it could be all three, reservoirs, gravity, or pumps, but how the system works. So that'll come up under the topic of hydraulic grade lines, and then how we design our pipeline layout, and then some of the risks with excessive energy. You know, if a little energy is good, a lot can be a problem. Obviously, too little energy is a problem as well. So we're going to try and cover off all of those areas and in the next 2 hours. So again, if you have any questions or you know any examples of some of the concepts that we're looking at, please feel free to send them through via chat. So that's kind of the agenda today. But first of all, we start with pressure, or the amount of force that we have acting in our system. And of course, that varies throughout the system. And so we want to look at how much pressure, how much force is in each area. So if we have a distribution system that is varied in elevation from sea level all the way up to the top of a hillside or up a hill and then down a ravine, what you'll know by putting a pressure gauge on fire hydrants at any of these locations is that the pressure is different. And that is all a function of elevation. Obviously, you know, there are a couple of very good reasons we need pressure in a water system. One, if pressure is applied at source and is forcing water through a distribution system, the pipe wall and the pressure itself acts as a barrier to contaminants. And typically the best run water systems employ what we call the multi-barrier concepts or philosophy to protecting against waterborne disease. So the pressure itself, forced up against the pipe wall, regardless of size of pipe or material, ensures that contaminants cannot enter in. And you think about it, even when a pipe cracks or has a pinhole due to corrosion, as long as water is being forced out, contaminants can't get in. Now, we don't want cracks in the pipe. That's a lot of waste and cost to a utility to repair it. However, it's still better to have positive pressure, as we call it in the distribution system, in order to prevent contaminants from getting into the system. And of course, it's how we deliver it to all of the ends of the distribution system, whether it's commercial, residential, institutional, industrial. We need the pressure to deliver that water from source to tap. You know, and that's a little different than our sewerage and drainage systems that typically flow at gravity. But, and we have lots of agricultural systems that work on a gravity basis as well, that collect water, surface water, through ditches and impoundment areas, and then deliver water as well. But in a distribution system, a basic requirement is that we pressurize the system in order to deliver safe water to the customer. Typically in a metric system, we're defining units of water pressure in kilopascals. Pascals are so small, you know, 1/1000th of a kPa or kilopascal, but that's how we measure it. You may have heard or come across pounds per square inch or PSI, or some of your suppliers might even deliver pressure gauges and monitoring equipment that have imperial measures on them. So pounds per square inch is the imperial. The conversion there, converting between metric and imperial, basically 1 PSI is the equivalent of 7 kPa, 6.9, 6.89 kPa. And the reverse then, 1 kilopascal is the equivalent to 0.14 PSI. And remember, those units are the same. If I fill up a jar with water to the equivalent measure of 1 PSI, it's the same amount of, or volume of liquid, 1 PSI to 7 kPa. Typically, we are working in metric and we'll stick with that. But they are different measures of the same concept, in this case, pressure. So imagine water standing in a jar, in a glass, or basically imagine a piece of pipe in the ground suddenly lifted up vertically, and it's clear, see-through, plexiglass, and you can put gradations on it. Basically, what we're talking about is imagining that pressure is elevation or head. And as you can see in the chart there, 1 foot of head is 0.43 PSI. The reverse, 1 PSI, 2.31 feet of head. But the metric pieces of this are 1 meter of head. So water in a cylinder, 1 meter in depth, the pressure gauge, if it's sensitive enough, will read 9.8 kPa. And if it's really sensitive, 1 kPa would measure 0.1 meters of head. And that's all we're dealing with. It's really that simple. Elevation can be converted into measurements of pressure, typically in the metric system in kPa. So imagine it's then, and we'll talk a little bit more about this when we look at hydraulic grade lines, but what we are doing when we deliver pressurized water through a distribution system is designing the system so that it is adequate amounts of pressure. And if you look around and you see higher buildings or changes in topography that change elevation, the energy has to be higher than that highest elevation. Otherwise, those delivery points get no water. There is no way to deliver water at a higher elevation than what your system is delivering. And that's really what we're doing when we design our water system. our engineers design capacity and energy to be delivered via different means. And later in the course, when we talk about pumps and motors, we'll talk about how we boost energy in a system when gravity may not be sufficient, or if we're pulling from a lake at a lower elevation up an elevated to a community elevated on the hillside, we boost that pressure. But really what we're doing is adding elevation. Remember too that it doesn't matter the shape or size of the water, the vessel. So if you look at the slide, whether it is a 5-meter diameter, 20-meter diameter, or half a meter in diameter, the vessel, if it's filled with 1 meter elevation of water, 1 meter of head, you will get 9.8 kPa, which is important because if it did rely on the size of the vessel, then our systems would have to be designed very differently. Now, we may want the larger reservoir that you see in the middle of the slide for very good supply reasons, right? The community, the number of connections, the demand on the water system is such that we need more water. But more water is not related to head or pressure. So we can do both, obviously. But when we're talking about head and static head, which is basically water sitting still, it's not moving through any pipelines, it's just basically poured into these vessels, 1 meter equals 9.8 kPa. So the relationship is the same, it doesn't always have to be 1 meter. And we can do it both ways. So actually, let's look at the second example first. Convert 7.2 meters of head. So instead of 1 meter of elevation, we have 7.2. We know the relationship from the previous slide is 1 meter to 9.8 kPa. So 7.2 meters in height, in elevation, in any of those vessels would translate to 70.6 kPa, right? We just multiplied by 9.8. And if we can do it one way, we can reverse it the other way. If the pressure gauge, and this is typically how operators look, they read a gauge, it's got to read out. In this case, the example is 66 kPa. All right, well, how many meters of head is that? 66 times 0.1 equals 6.6 meters. And it's almost a 10-to-1 relationship, right? 9.8 kPa per meter, or 0.1 meters to kPa. So when you're looking at a pressure gauge, next time you're out in the field and you read a pressure gauge at a reservoir, or you're servicing a fire hydrant and you put a pressure gauge on it to see the static pressure or the static head, you will read, say, 660 kPa. Okay, now you know it's almost a factor of 10. All right, so now I've got 66 meters, which means I really have 66 meters of elevation. I can imagine that where I'm actually working at that moment. So it's a really good exercise. I suggest to operators to practice doing that because it really helps get a sense of what is the energy that I have available in the system. And then how do I deliver it? Because there are lots of things operators do that can affect that available energy, right? You could close a valve that you're not supposed to. You could, or throttle a valve, don't completely close it. So now the supply is restricted, the velocity increases, and the energy decreases. So it's a good way of understanding how the energy in your system not only is created, but how it's delivered. And these are just examples of that. This one is, the next question's in imperial, but the same principles follow. 425 feet of head is so many PSI, and the factor, and remember these equations are all on your, will be on your formula sheets for the exam, so you don't have to memorize them. They will be available, and it's just basically like we were talking last week with math, just plug in the numbers. And 70 PSI to meters of head Here we're actually moving between imperial and metric, which means that, again, the actual elevation hasn't changed, just how we express it. 70 psi times 7 kpi or kPa equals 490. Now we convert, so we basically have the second calculation to do to get 49 meters of head. But the real key to remember is the relationship between head and elevation and kPa or psi. So knowing the difference in elevation can go a long way to determining what the height of the water column is. And the slide gives a couple of examples. So the water tower in our little community here is full of water. And if you're standing at the front door of the house on the left with the pink roof, 93 feet, but because of the elevation in the community, the topography, I have 40 psi on my pressure gauge. I go down the hill to the next house, and that person has 65 psi. The water level in the tower has not changed. It's simply the effect of head of elevation working on that plumbing at that point, the water system. And if I go further down the hill, this guy's got 80 psi, so he can knock his neighbor's cat off the fence if he wants. The water level in the tank hasn't changed, but he now has 80 psi, so double. And all of that is a result of change in elevation. So as an operator in a system, you may have areas where the pressure is really good and your customers are happy, or up an elevated area, the pressure starts to diminish. And this is assuming all the pipes are wide open, all the valves are properly operating, the pipe are in good shape, they're not corroded, because we're going to talk about the effects of the pipelines themselves on pressure. But in a brand new system, the only difference in delivering the different readings on a pressure gauge is elevation, is the height of the column of water. Okay, so that's the important concept to remember. And you can do that same estimate wherever you are in the system without seeing the tank or the pump, just by putting a gauge on a hydrant or on a tap at a place of business or a resident if they're complaining about low pressure. You can actually, you don't have to tell them there's only 20 meters of head, but you will know that just simply by making the calculation off the gauge. Here's a couple of other points or examples. And again, the reservoir at the top of the hill fills and empties. So at different parts of the system, these pressures will be that much more. So higher pressure in the lower elevation areas in your community, lower pressure at the high points, and then of course at the valley bottom, highest pressure. And the example is given based on the reservoir containing 3.3 meters of water. And there will be math questions like this on the exam. So the question might be, what is the pressure reading on a gauge in kPa at a house that is, well, like this, 73 meters for point B below the bottom of the reservoir? All right, well, now I have to add the 3.3 meters of water. It's always good to draw it out so you can visualize it like this slide, because all you're doing is looking at the elevation change, and you're either adding or subtracting in order to get the reading on the gauge. So basically, the question, what are the estimated pressures at the bottom of the reservoir, point B, C, and D? So B, C, and D. They've given us enough information to solve, right? We've got point A is 872 meters. Now this would be above sea level. The reservoir contains 3.3, so that would add 3.3 to that. right, to get to this line here. And now we look at the different elevations from each point. So, for instance, the bottom of the reservoir contains 3.3 meters of water, which translates by multiplying times 9.8 kPa is 32.3 kPa. And then we look at point B. Again, all we're doing is changing the elevation. 73 plus 3.3 because we have 3.3 meters of water in the reservoir. And then we create 76.3 meters of head. So don't worry too much about converting from kPa to PSI. You're going to be working in metric. So stay with the metric calculations. And basically, the easiest way to solve these problems is to look at what they're asking, draw it all out, and then do the math based on the relationship of kPa to meters of head. And then again, point C and point D. So we're not, I mean, you'll have this slideshow so you can work this through. And the fact you have the answers, you can see and work it backwards as well. But here's the key, 9.8 kPa per meter. So as long as you get the right elevation in meters from the measuring point, whether that's the bottom of the reservoir, the top of the reservoir, they could ask you whatever. They could say the reservoir is half full, but it's 6 meters high. Okay, now you know it's 3 meters. And then you can do your calculations from there. So just work at it sequentially from that point. So for example, the relationship again, if your pressure gauge reads 860 kPa, what's the head in meters? Well, we know that when we're working with kPa, it's almost a factor of 10 exactly. So 0.1 is almost the exact same thing. There's a couple of decimal points there of dividing by 10, 86 meters of head. So that means that at the gauge, there is this invisible column, but it's there. That's how much. So it would be the same as someone takes clear glass tube and stacks it all, connects it all up vertically, 86 meters, and then asks you to hold the bottom of it. There will be 860 kPa acting on every aspect of your hand, right? That you won't be able to hold it. Right? The pressure at the bottom of a 50-meter high tower is 330 kPa. How full is the reservoir? Well, we know again, times 0.1, the reservoir is 33 meters full. So, okay, it's not overflowing because it's a 50-meter high tower, but it's always the same relationship, right? kPa to meters of head is times 0.1. Going the other way is 9.8 meters to kPa. And it's useful information for operators because it gives us the understanding of how our system has created and is delivering the energy required throughout the system. So, and this is typical when you're an operator. When standing beside a fire hydrant with a known pressure of 600 kPa, what's the pressure of a house 30 meters below you? So if we're going further down, we either are adding or subtracting energy. But we know that the energy is the tower or the column of water represents close to 60 meters of head. If we're adding 30 meters in depth, right, instead of subtracting, we get 894, almost 900 kPa at the fire hydrant. And there will be math questions like that, where you will be given an elevation, and they'll ask what the elevation is, or the kPa, at this different point. At that point, you really only have to add or subtract. But if you draw a picture and realize that the top water level of the reservoirs here if I go lower in elevation or add another lower in topography, then I know I'm adding that together. If, in fact, I'm going to higher ground, I'm actually subtracting it because the pressure gauge will have less of a column above it. So drawing the picture really helps. I've certainly found that. So another example, the base of a 30-meter high reservoir, okay, so we know the reservoir is 30 meters high, is located 50 meters above sea level. What's the pressure at sea level? If the reservoir is half full. So they're trying to confuse you. So the reservoir is 30 meters, 50 meters above sea level. So now we have 80, but the reservoir is half full. Okay, so draw it out. There's our 30-meter reservoir, 30 meters. It's only half full, so that's why the red part, it's empty. So that makes it only 15 meters, 50 meters above sea level. So we now add the 50 and the 15. 65 meters times 9.8 kPa. And remember, as long as we're dealing with a vertical elevation or column of water to create the head we need in the system, if our elevation changes and starts to climb, we know we're subtracting. If it goes further below, we're adding. So again, if your pressure gauge reads 970 kPa, how many meters below are you from the top of the storage? Well, there's our visual representation. Basically 97 meters below the top level of the reservoir. And remember to read the question carefully, because sometimes they may say, like that previous question, the reservoir is only half full. So don't add the whole 30 meters to the 50 meters because there's no water there. You're dealing with the 15-meter mark. So always helps to draw it out. But again, you're visually representing the elevation that has been established to create the energy in the system. The next question, static pressure in a pipeline is 940 kPa. All right, what elevation of water do we actually need to create that pressure? So that's what it's saying on your pressure gauge, 940 kPa. 940 kPa times 0.1 equals 94 meters. And remember, like all other math questions, once you get the answer, you can solve it back the other way just to see if it's correct. Just to reinforce the concept of elevation. So now we've got to get that water from the reservoir or from source to our customers. So when we fill the tank and it's sitting in the tank and the valve is closed, that's static. That's our elevation, that's our gauge on the hydrant or at the outlet of a reservoir or tank is telling us it's static head. But now we've got to send that water to our customers. So that's what dynamic head means. We're moving water through the system. So when water moves under pressure through a pipe network, there are other forces at work. The water pressure at any point is equal to the static head, which is that amount of energy that we've just been looking at, plus or minus head losses, usually minusing head loss. And head loss, the shortcut is basically friction, right? It robs energy from the pipe and from our system. And so there are these factors that come in. And as we go through and look more detailed at the operations of the water system and look at the materials that are used, we have to be very careful about the materials that we select, because the rougher the pipe, the higher the head loss. Think of it as actually scouring away the energy, robbing the energy from the system. bends in the pipeline. Every time you make water under pressure turn a corner, whether it's 11¼ degrees, 45 degrees, 90 degrees, we lose a bit of energy. Your customers sometimes will complain that we have so much energy at the road, but then it's a long run of, say, small diameter copper or plastic pipe that gets to the customer's house. So even when there's no elevation change, it's at the exact same elevation above sea level from the water main to the customer. But if you go far and far and farther away, there'll be no water left. Friction loss will consume all of the energy. And so when your customer turns on a tap, there's nothing there. And that's strictly head loss, right? The elevation hasn't changed, but head loss has overcome the static head in the system, which is why engineers then design different diameters of pipe based on how long the service is going to be and how much water the customer needs. But just as an example, when I was working in North Van, we had lots of elevation changes, but there were several times when these larger properties got developed and the customer from the road to the house was so far back from the road, ran too small a service line, and this was a long time ago, so they were using 1/2-inch soft copper. And by the time the plumber hooked up at the side of the road where our curb stop was left, by the time the plumber got to the house, was basically a trickle of water left. So they thought that we had done something wrong when we tapped the main, and there was, we hadn't tapped it properly, so there was no water coming out. No, it's simply too much head loss. And the American Water Works Association has all the tables in their standards to show different types of pipe, material, and diameter combined to create certain amounts of head loss per 100 feet or 30 meters of pipe. So imagine a 2-inch water line crossing a road to a business, and then switching that out with a 1/2-inch line. Same distance, same business, same elevation, a lot less energy, not the amount of water, but you put a pressure gauge at the house or the business, it will be different based on head loss. So head loss is really critical. We have to manage that when we're designing and operating our water systems. Because if there's too much in the system through a combination of bends, old pipe, corroded pipe, perhaps valves that have been exercised and not reopened properly, we end up starving the system of energy. So if you had all day, imagine a 45-gallon drum or a barrel, and you want to fill it, and you have totally unrestricted flow with 90 meters of elevation. You're filling the barrel 5 seconds, 10 seconds. Switch the pipe to a smaller diameter pipe or badly rusted galvanized pipe, or one where the valve is 3/4 closed. It might take all day to fill it, right? But when you put a pressure gauge on it, it'll be the same. There's just no, or it'll be the same under static conditions, but as soon as water starts to move, that dynamic condition, the energy is robbed. So from an operations perspective, it's not just about building the reservoir high enough or sizing the pump appropriately. Every connection along the line between the supply and the customer has to be taken into consideration. And as operators, we can impact all of this on a daily basis. If you shut the wrong valve, or if you close a valve and think it's open, but it really isn't, or it hasn't been opened all the way, that can affect your customers in terms of the hydraulic capacity of the system. So that becomes really critical. And here's an example visually of dynamic head. We have a reservoir, 30 meters to the bottom of the reservoir from our pipe. we actually can calculate the head loss in that 1.2 kilometers or 1,200 meters of cast iron pipe. And we say, okay, we can actually calculate, and you won't be asked to do that, but engineers do through tables based on the size of the pipe, the material of the pipe, and the degree of the bend, can calculate head loss. And of course, the higher the energy, the more there is to lose of it as well. So we can actually calculate how much head loss is through each of these features. The reducer, where we switch from, say, 200 millimeter down to 150, 90-degree bend, and then a valve that's been throttled, which then increases the velocity, but it robs that pipeline of its energy, which then becomes a real problem for operators, because we do not want, in an ideal system, we do not want the energy in the system being robbed so much to the point that some of our customers can't use the supply, or it goes negative and you actually have the potential for backflow or cross connection. So what we're looking at when we're calculating dynamic head is, all right, the static head is when the reservoir, no demand on it. There's no flow through the pipeline. But as soon as we open the valve at the base of the reservoir or in the pipeline itself, we now have dynamic head. We have water moving through the system. And now we have head loss. In other words, friction from a variety of factors can act upon that energy. So dynamic head is never as high as static head, simply because there's always some form of loss. So you can see here in the example, 30 meters at static head. But as soon as the water starts moving through the pipeline, now we have head loss. And we have that head loss in a variety of areas, whether it's the bend, whether it's the reducer, or the closed pipe. And so they've actually calculated in this example 6 meters, 6.6 meters of lost energy. So even though you think you have the full 30 meters of dynamic head, you're actually only, of static head, once you start moving the water, you're only at 23.4. Now, depending on the size of the distribution system and the amount of bends, valves that have been partially closed, tuberculation or corrosion, that can actually be a real problem, because it will no longer, the energy is no longer there to assist the system to deliver the water in the volumes that were designed to be delivered. So we minimize head loss by either straightening out the pipe, increasing the size of the pipe, or making sure our valves are closed. Some of that is done at the design stage by engineer. They design a 200 millimeter pipe for the system as opposed to a 150, based on expected demand and flows, etc. But as operators, okay, making sure that we don't leave valves closed is critical, because one valve by itself, well, could be a problem. More than one, or one valve in a critical location, can basically negate the entire supply. And then the fire department doesn't have enough supply for an emergency, or the agricultural sector or the commercial sector can't do their work because the way the system has been not configured, but operated. So it becomes really critical and very easy for operators to overlook a broken valve or a closed valve, or a system that hasn't been flushed for many years, and then corrosion builds up, that sort of thing. So it becomes really critical in terms of looking at the sort of the efficient operation of a water system. So we talk about head loss as anything that will rob energy. So our potential for static energy versus dynamic when water is moving. And one of the ways engineers look at that is by designing pipelines and choosing pipeline materials that have very high Hazen-Williams factors, or C factors, which are roughness coefficients. So imagine if you cut open a section of water main The rougher or the more corroded the pipe wall is, the more head loss. And it kind of makes sense. When you look down the barrel of a pipe, say a 2-inch galvanized pipe that's been in service for 40 years, yeah, you're not expecting to see a smooth pipe wall. You'll see iron deposits and tuberculation, maybe some sediment. And now that 2-inch pipe is actually behaving as if it was a 3/4-inch pipe. Pipe's still the same on the outside wall, but the corrosion has built up to the fact that now the pipe wall is rougher, which means more head loss. So the C factor is that calculation that engineers and designers look at based on the type of pipe material. So in many ways, you know, the rougher the pipe, the lower the number. And so I've seen old cast iron that we did flow measurements on, and it really had a C factor of about 36, 37, which is terrible. I mean, cast iron, when it was brand new, put in the ground 80 years ago, would have been at 100. So it's not just that you don't get good water, aesthetically pleasing water, it's hydraulically no longer acceptable. So you either replace the pipe with, say, a PVC or a high density polyethylene, which could have a C factor of about 140, which means more of that pipe energy, the pipeline's total energy in static head, as it flows, more of it is delivered to the customer. So the rougher the pipe, the lower the coefficient. Here's the formula. You're not going to have to calculate that, but it becomes critical when building out systems or deciding on what pipe to use to upgrade older systems. Here's a table showing the variety of C factors and the range of C factors. So if you have asbestos or AC in your system, new AC can be as high as 140. And remember, the higher the number, the better. It minimizes head loss. So it preserves that static head that you started with. Let's see, cast iron. So a new unlined 130, which is quite optimistic. 20-year-old cast iron is starting, you can see the numbers start to go down. 40-year-old, 60 to 80, 64 to 83. As I said, we where I used to work, we had some cast iron that was only 50 years old, but the C factors weren't even 40, which means that it's no longer acting like a 150 diameter or a 200 diameter main. And here are the different types, like copper, galvanized, and so on. And this is new, galvanized iron 120. So when a pipe is new, smooth, put into service, the question then is, and when we talk about operations, we'll look at that some more. What is it about your system in terms of its age and its characteristics that can actually lower that C factor? And a lot of times it is just age, but could be aggressive water, pH, high presence of iron bacteria in the system, especially if it's got a lot of iron or steel in the main and the pipe in the system. So we want a high C factor because then we minimize or preserve the energy in the system. Okay, so what's an acceptable pressure in the system? Well, the American Water Works Association suggests the lowest acceptable under normal operation would be 140 kPa or about 20 psi. And so think about the highest areas of elevation in a distribution system. There needs to be enough energy to get from point A to point B and any elevation change and still deliver 140 kPa. So engineers will decide what pipe material and diameter needs to be installed. They may need to decide on putting in a booster pump to boost the pressure, because otherwise you don't have enough for protecting water systems in emergencies like fire. Now, on the other hand, you don't want too much pressure either, because that can damage not just your customers' plumbing, hot water tanks, and fixtures, but at high pressure, it actually shortens the life of your pipeline. Because imagine high flows moving through a pressurized water system, and the higher the pressure, that means, we'll talk about thrust in a little while, when water changes direction, the effects are even greater, amplified, and it starts to shorten the life of the pipeline. So as an example, where I used to work in North Vancouver, side of a mountain, there needed to be enough energy for the highest level of the community, but that meant at the lower end of the elevation of these pressure zones, the pressure was pretty high, and it got up to, well, close to 200 psi. And that would damage not only residential and business plumbing, but also meant more water main breaks or service blowouts, that sort of thing. So you do not want excessive pressure in the system. So there's this balancing act between creating enough static pressure, static head and elevation, designing the system so you don't rob it of that energy along the way. But if you have excessive elevation changes, you don't want to overpressurize the low areas, and you don't want to underpressurize the high areas. So we'll talk about ways of doing that, whether it's pressure regulators or altitude valves or pumps as we go into operations. But it's all tied to the same concept of elevation creating head, static head. And then once we start moving water through the system, and think about it, systems are always moving. Once you've filled a reservoir, there's demand. And so water is constantly moving. Well, how much is the head loss? How much energy are we losing? There's a picture of a regulator, which may be on the inlet side where a customer's connection either connects to the city at the curb stop or in the house, and basically is set to, if the city is delivering 60 psi, you might be dropping it down to 50 psi, that sort of thing, just to protect the internal plumbing. And remember, we've talked about changes in the pipe condition or size, but lots of things can happen, as operators know, that can drop the energy in the system. So, picture there of a fire being fought. Obviously, we want our fire departments to have adequate head or adequate pressure to be effective in fighting a fire and putting out emergencies that might pop up. But depending on what time of day or time of year, that amount of flow going through one or multiple fire hoses can drop the energy, and could be areas of the system that have no water while a fire is being fought. When the weather is good, customers use more water. In this part of the world, summertime usage is almost double that of winter. And the estimate from the local regional district here is that outdoor use of water, which is gardening, we're not talking commercial, just residential, gardening, washing a car, irrigation, that sort of thing, that represents 40% of most people's water bills. So the system has to be built out to compensate for those periods of high demand. And a lot of times the system was built up long before there were a lot of people living there, or that long before they had a lot of gardens and built up or infill that there are now two houses where there used to be one. So utilities will enact water conservation measures. And that's not just to stop the amount of water moving through the system or lower it, it's to preserve the energy in the system. If everyone is washing their car at the same time and sprinkling, and yet you still have a fire, because that's typical. An emergency situation isn't happening when no one else is using water. Can the system support that kind of a demand? And we're talking about not just the amount of water that can be delivered, but the energy that it delivers it at. A water main break. You've all seen car chase movies, and almost inevitably they hit a fire hydrant and water goes everywhere. Okay, well, what happens then in the rest of the system? Hopefully that's for a very short period of time. The waterworks operators shut off the fire hydrant so that it doesn't create property damage. But while that excessive flow is happening, the energy in the system can drop. Water main break, same thing. So we want to make sure that our system is designed to minimize those events. And it's not just the volume of water that we're sending through the system at that time, it's what it does to the energy. And if we drop the energy too much, we can actually reverse the flow, right? And you get cross connections or backflow prevention, backflow situations. And so we need to prevent that from happening. So the best designed system provides adequate head energy for all conditions. We take into account emergencies, take into account seasonal changes in demand. We take into account potential drought. All of these are built in. And then our systems age. And they become 10, 20, 30, 40, 100 years old. And more people are added to the community, whether it's, as I said before, one house becoming two becoming four, apartment buildings where there used to be single family or where it was an open field or meadow. All of that can affect the energy, not just the volume of water, but the energy at which it's delivered. So that becomes really critical. So basically, in extreme situations, as the slide says, residual pressures could drop to zero. And we never want that. Think of the tide going out, right? We'd never want the tide to go out in our water system, because when it comes back in, it's full of things that could make us sick. We also could potentially create a vacuum. And there are videos, if you go to YouTube, you can watch tanker trucks being filled, and all of a sudden there's a vacuum and the whole tanker truck collapses. There's probably videos of water mains doing the same. The American Water Works Association used to show pictures of a steel transmission main, multiple kilometers long, without sufficient air valves to prevent the vacuum. And steel, by its nature, how it's made, it just flattened and became flat as pancake. Well, you can't blow it back up. That was a huge, and I can't remember what state it was in. It was like Colorado or something. It was like 40 years ago. But steel water mains will collapse. Vacuum is a potential problem. So later on in the program, we'll talk about valves and their selection and usage and sizing. And air valves are critical, because when there's a water main break or high demand, if the grade line drops, to prevent a vacuum, air needs to be brought into the pipe. But negative pressure means that the energy, that column of water, 30 meters, 40 meters, 90 meters high, is now below the actual service connections to our residents. So picture a subdivision on the top of a hill. And at the bottom of the hill, there's a fire hydrant, and the city crew comes to flush the water main, and they open up the water main, the pumper port, 4.5-inch port, full blast, and then next thing you know, the office is getting a bunch of phone calls from those houses up in the residential area saying, we got no water. That's the energy that has gone negative, because they're now basically like the tide going out. They're stranded and have no possible way of getting positive pressure into their system. So one thing, if a car hits a fire hydrant, you know, like in the Bruce Willis movie, one of the Die Hard movies, he actually aims his car at a fire hydrant and knocks a guy out of a helicopter. That's because he understands hydraulics. He's not just Bruce Willis, the greatest actor the world has ever seen. He's actually a waterworks operator, and he knows that if he hits that fire hydrant, there will be so much energy available to actually weaponize it, knock the guy out of a helicopter. Highly recommend that movie. Anyway, if you don't have that energy available, then we create a problem. So one thing that an emergency can do, you can isolate it and restore the grade line. But if it's demand, if it's hot weather, agriculture, or different population growth, we need our engineers and our system designers to have taken that into account so that the line pressure never drops below that minimal level of 140 kPa. And if you can't guarantee that, most cities in North America have adopted what's called a cross-connection control program to prevent that water that we are delivering to the customer from going the other way, right? We're quite happy to deliver water to our customers. We are never happy when the customers want to give it back without some form of cross-connection control. And we'll talk about cross-connection control again, but it becomes critical for the water quality, but it really arises from the hydraulic configurations of our system, and that static pressure, static head, once we start moving that water through the system, there's no longer sufficient energy in the system for these reasons that we talked about: the pipe being corroded, the pipe being too small, a valve being left shut or broken shut or throttled. All of these reasons can create excessive head loss that can lead to a negative pressure situation. And as operators, you know which areas of your system, as it says at the bottom of the slide, traditional areas of low pressure. You may have high pressure areas, but low pressure areas we typically are aware of for a variety of reasons. And we set up our operations around that in areas where we had low grade lines and lower pressure close to that 20 psi or 140 kPa area. We would actually forbid other departments from using water. You can't hook a street sweeper hose up to fill a tank or a sewer flusher because of the potential for dropping the energy to an unacceptable level. So we said you can use the fire hydrant over in this neighborhood where we have lots of elevation and lots of energy available. So here's an example of back siphonage. And this is a natural cause. A water main breaks, and because of the outflow from the broken pipe, we actually can reverse flow from the water service and pull it from the bathtub. Could make someone sick, and we can do that on a much larger scale as well, whether it's a break in the pipe or high demand, like a fire hydrant being turned on full. So that's called back siphonage, and we have to protect against that. So we talked about things that can rob, or conditions that can rob energy. Well, the reverse is true. We have means at our disposal to increase elevation artificially. We're not actually changing the elevation of the pipelines, but we can boost energy by installing a pump. So wherever the energy is chronically low, and it may be seasonal, it could be just in the summertime that the energy is low, then we design a pump to be installed so that at a certain set point, the pump will come on and raise the elevation again for the customers that are downstream. And we do that in lots of locations where, in fact, there are elevation changes just even within a neighborhood. They may be very small inline boosters, or they may be large turbine style pumps to pump to another reservoir to create elevation that way. And what we're talking about is, and you'll see this on the exam, you'll be asked to define what is an HGL, hydraulic grade line. So what we're looking at is a way of visually or graphically representing what the head in the system is at any point in the piping network, right? So remember, at static, if it was a perfect system with no friction, you would have a 30-meter high reservoir. And while it's isolated, and imagine zero leakage, nothing moving, that grade line would move through the system and it would be perfectly flat, flat as a table. But as soon as water starts to move through the system, the grade line starts to slope, and it represents how much energy is being lost as water is delivered to a customer or customers. And again, all those reasons still exist. Bends, closed valves, undersized pipe, corroded or rough pipe walls. But we can calculate that. And we could actually, if you imagine going into 6 blocks of your distribution system and putting a pressure gauge as you move away from, say, a reservoir or a pump, and as you move away, you put a pressure gauge, and then a block later, pressure gauge, and a pressure gauge, and a pressure gauge, you could actually take those readings at the exact same time. And because we've done the math, you could calculate the meters of head at each location. And then you could actually, at that top level, you would have a dot, you could connect those dots, and you would have a hydraulic grade line. The example I gave earlier of a clear plastic tube tapped into a water main every block. So imagine a single pipe moving from a reservoir to, say, a school a mile away or a kilometer away. No other pipe, no other T's or branches, just one pipe. And every 100 meters out of that kilometer, you tap the water main and put a pressure gauge on it. And at the same time, put a plastic tube, clear plastic tube. You would actually could mark where the water stops, because the water is going to stop eventually at the top of the energy, right? As soon as it loses energy, you could draw a mark on that tube and then connect them all up, and that is a hydraulic grade line. And anywhere in between where you're standing, you know, if you ran a string between them all, you'd be standing underneath that string, looking up and saying, okay, that's exactly how much energy I have in my system. And then you turn on a tap at the school, and the grade line will change, and it will start to lower, and you'll see the pressure gauges closer to the school have a slightly lower number or lower reading based on how much flow is moving through, based on the size of the pipe, based on the age of the pipe, and if there's any valves in between. But the hydraulic grade line always slopes away from source and toward where the flow is going. And it actually shows, sometimes we call it a hydraulic slope. And when you're working in wastewater, we calculate slope all the time, rise over run, to determine what our slope is in the system. A hydraulic grade line does the same, but it's on a pressurized water system. And what we're determining is, do we have enough energy to actually deliver water to all the parts that need it? And think about it over a 24-hour cycle, a diurnal cycle. In the winter, in the summer, maybe you don't have much of a winter, but high demand and low demand, that grade line will shift. Up in this part of the world, there are a couple of ski resorts, and in the summertime, their grade line's pretty good. But because everyone, except for COVID, everyone shows up there in the winter to ski, well, now their grade line crashes because everyone's using water at the same time. The joke is, the Super Bowl's this Sunday. Go Chiefs. Grade line's going to crash. Now, most systems are designed that they can handle, everyone at halftime using the bathroom or, mixing drinks and using the sink. But it's the same effect. Do you have enough energy in your system to handle all of the design flows, the estimated flows, and of course, emergency flow? So there's an example of a hydraulic grade line. So 100 feet, so 30.5 meters from one location to another. Flow is going from your left to your right. There's your pressure gauge. And you can see the grade line sloping. Now, How much it slopes will be based on the size of this pipe, the condition of the pipe, that sort of thing, and how much demand is downstream of the system. But the key here is the grade line can actually be represented simply by looking at the reading of the pressure gauge and imagining the column of water above your head. And so at the start of the location, we're at the source, say, where the first tube has been connected, here is our grade line. 100 feet away, or 30.5 meters, the head loss, based on what the gauge says, and it would be the gauge in these two locations, and looking at the difference, we can actually calculate, because remember, if we can calculate it in kPa or PSI, we can translate that into elevation. So we actually have 5 feet or 1.5 meters of head loss. And so if we connect that point to the source, there's our grade line, there's our slope. Now imagine if your city, and not much of a city in between 100 feet, but any building in this area between the grade line and that original line, the 5 feet, would have zero pressure. We wouldn't have any water. So it becomes really critical that our grade line is as flat as possible, because what that means is we're preserving energy. The steeper the grade line, the more it slopes towards the customer, the more energy is lost. So example that I gave earlier of the house in North End that was being built. The city came and tapped a 3/4 inch water service at the main, rolled out the copper across the street, and left it at the curb. And the street's a 20 feet, 6 meter right of way. But the house was set back 160 feet, something like that, maybe close to 200 feet. And they ran too small a pipe. Wasn't even up on a hill, it was just flat. But the head loss, which is that line, the gap there, was so great that the grade line actually dropped and stranded the 2 top floors. It was a 3-story house. The 2 top floors of the house had no water, simply because of the grade line collapsing so far. So as operators, we got to think about all of the things that we do, or the conditions that our system has built in that can, how should we say, sacrifice energy. And it's all about preserving as much energy as possible. Here's a couple of other examples. The pipe is actually going uphill. The grade line will still slope away from the source or the supply. Or as it says in the slide, the direction of flow. Which is important because, you know, a lot of cities build out from the center and their supply might be there. So we might have to build an elevated water tower or a pump in order to bring that grade line up. Now the grade line is still sloping away, but as soon as the pump enters the system, the grade line jumps and then slopes away again. But it may be sufficiently high or boosted pressure in elevation to guarantee adequate supply. Oops. So here's another example. The hydraulic grade line from the source, direction of flow here, is still sloping away from source, but we're filling a reservoir. And so if we're able to fill that reservoir to the top level, that will start to flatten out the grade line as long as this reservoir is open to the supply. If there's a check valve here that prevents flow from going backwards, grade line won't change. But what we can do is boost that in. Here's an example of the reservoir emptying. Right now, it becomes the source, right? So if a check valve, we fill the reservoir, grade line slopes away from the source towards the reservoir. Pump turns off back here and the reservoir starts emptying. We actually can shift the grade line. This is an exaggerated example, but what we can do through a variety of means, whether it's elevated storage, whether it's a booster pump, is we can bolster that grade line. Here's a good example of an actual dynamic situation. So our reservoir on the right-hand side here is full of water. And here's the normal, the dotted line is the normal grade line. That's how much energy we have available. And remember, whether it's at the house or if there's a fire hydrant along the way, we can actually imagine or calculate what that line is just by the reading on the pressure gauge. Then somebody's barbecue or kitchen catches fire. Fire department arrives and hooks up to the hydrant, and boom, grade line crashes because of the high demand exerted by the fire. And Joe's house here is now, under normal situations, has got plenty of energy to provide water all through the house. But because of the hydraulic grade line crashing due to the fire, due to the high demand, top floor of the house, no water. So again, we can, whether we stuck a clear plastic tube here and here and here, all throughout the system, we could actually create a visual representation of that grade line physically. Most of the time, we simply do it with a pressure gauge. And that is why it's really critical for operators to see the readout on a pressure gauge in kPa or PSI, but kPa, and actually translate that into available energy. Because remember, as soon as we turn on a tap, basically water is moving. So as soon as we go from static to dynamic, hint, always, we're always under some form of dynamic head. It may not be very much in the middle of the night and no one's using any water and it's just the drip, drip, drip of a leaky tap, but that's still dynamic. We're still moving water through the system. We want to keep that grade line as flat as possible. Okay. The next example, the drawing down below, shows flow going from left to right. And you can see the hydraulic grade line, and all of a sudden it encounters a valve that's not quite open all the way. It's throttled. And that's actually what happens. You could take a pressure reading on the outlet side or on the right-hand side of the valve, and on the left-hand side, and connect your clear plexiglass tube, and you would see this grade line dropping drastically because of the restriction in the pipe. And hopefully that wasn't you, the operator, that left that valve half closed. Later on in the program, we'll talk, in the weeks ahead, we'll talk about valve maintenance and the importance of recording every time an operator touches a valve. And also making sure that you, in your utility, your operators are the only ones that are allowed to touch the valve, because contractors or plumbers or homeowners even with access to a key to close or restrict the flow of a valve, that can create lots of problems, not just for the fire department, but just for the everyday operation of our systems. So I like these representations showing you that, remember, flow is happening at all times, so it's a dynamic head situation. And with our best intentions, we design our system to minimize how much head loss there is, based on the size of the pipe, the age, the type of material we use, and the valving that we install. And yet stuff happens, right? Fires happen, Bruce Willis comes along and hits a fire hydrant, all sorts of things that can drop that grade line to a point where our service suffers, right? And our customers don't get the supply that they're expecting or are used to. So we talked in the math, just moving on to the next concept of hydraulics. So we've moved from static head to dynamic head. And of course, as water moves through the pipeline, now we can start calculating the flow. And we did this last week, right? Q equals A times V. So flow in typically meters per second is a product of area, the cross-sectional area of the pipe in square meters, and the speed, the velocity that is flowing in, right? So that's how we get cubic meters per second. So we end up having a volume, cubic meters, over time, seconds. So if that is the case, if demand increases, then velocity increases. Okay, I'll say that again. If the demand, So our user at the end of the main increases, turns the tap half on to full on, velocity increases because area is still the same. But if the area decreases, i.e. shrinking the size of the pipe, all right, well, to maintain that flow, velocity has to increase. So in each of these two cases, velocity is increased, which in turn creates a greater amount of friction. Remember, the pipe size is based on what, in our communities, it's typically based on what engineers have determined will satisfy demand, not just under day-to-day conditions, but also under emergency situations. But the faster water moves through a pipe system, the higher the friction. And of course, that means more head loss. More friction results in additional head loss, which means the grade line is going to go from here to there, right? It's going to get steeper. So if the pipe is too small, or if we go from, in this part of the world, from winter to summer, and everyone's now using water, in other words, a higher demand, we can have a lower pressure. And it's not unusual in this part of the world to have pressure at the outside tap or at the fire hydrant at the street of 60 psi, 70, 75 psi, and actually have that drop by like 5 psi in the summer. Doesn't sound like much, but over a whole system, it's noticeable. So a lot of what our engineers are doing when they're designing and building our water systems is looking at the best ways, the optimal ways of preserving energy. Because you think about it, whether it's from a treatment plant or from a surface impounded area, a lake, we pay a lot of dough to get water not just clean enough and safe enough to drink, but in volumes sufficient for our supplies. And if we can't provide it, then the ratepayers are not very happy. And of course, if it's because of emergencies or breaks in pipes and leakage, that becomes another problem as well. So we build out our systems to provide a certain amount of energy. Our jobs as operators is not just maintaining, the system, the pipes and the hydrants and the water meters, but it's about preserving the energy in the system. It's got to be clean and safe to drink, but there has to be enough of it at the energy that the system was designed to do. And so I think it's quite useful for operators to think of it in those terms, right? We need to be able to provide enough water for what our customers are doing, whether it's irrigation, commercial, industrial use, or residential. So we size pipelines to meet peak demand. What is the peak demand? And in this part of the world, most areas in the northern parts of Canada, the United States, southern parts of Canada, northern United States, high demand is sometime in mid-August. That's the day with the highest demand. Whereas the ski resorts, it's typically New Year's Day or some time around Christmas time, where all of a sudden a community of 5,000 people becomes a community of 50,000 people because everyone wants to ski at the same time. So we, the engineers in, say, Whistler, where the Olympics were held, have a different challenge to meet the system design. And think about designing a system that, resorts have this issue where they may go up to 10,000 people, and the rest of the year, 8 months of the year, there's 2,000 people. Well, that means you've got much larger pipe or much larger reservoirs in order to meet those 2 months or 4 months of the year versus 8 months. So that means, okay, we've got different issues. Maybe we have issues around water getting stale or not enough flow. But for most cases, most cities, we have a max day demand. We have peak demand over a season. And we also then have to add in emergencies like fire or drought or other things like that. So we want to be able to keep the velocities low. The pipe is too small, velocity speeds up, you get these scouring velocities, as it says at the bottom of the slide there, once you get over 2.5 feet, 0.75, close to a meter per second, now you're at flushing velocities. That's starving a lot of energy. It's basically taking all that energy that you paid to put into the system, and now it's out the window because of head loss. And you don't want to scour water mains unless, like when we talk later about operations, we'll talk about flushing. Now, how engineers do that, again, preserving the hydraulics, preserving the static / dynamic head in the system. We want to keep enough pressure in the system to meet peak demands, to meet emergency demands, but also at minimizing velocity. Well, so we look at different ways of connecting the pipe. So we'll talk a little bit, yeah, we're okay for time, about branch systems. So there may be a couple of questions on the distribution exam, the difference between a branch or a tree versus a grid or an arterial loop. And remember, we're thinking about it not in terms of aesthetics, we're thinking about it in terms of hydraulics, adequate energy, preserving the energy in the system. So here's a branch or a tree. You can see the main trunk. So that could be a 250, it could be even an 200 millimeter pipe, it could be a 300, depending on the size of the community. And then the distribution mains that feed the customers are 150, typically 150, 200 millimeter dimension. And for the most part, the fire hydrants and the services are off the distribution mains, not off the trunk mains, because you want to preserve as much energy from left to right on the slide, from the source all the way to the end. And you don't want a lot of connection points on the trunk. Simply connect the distribution mains as you need them. So that's a branch or a tree, right? Most common in rural areas. Again, the grade line is going to be much steeper because you've only got the one supply, and then each branch is going to take a little bit of energy off that trunk, right? It also operationally, if you have to shut down the main upstream here, everything downstream is isolated. So that's a fairly steep grade line, right? It's now crashed to zero. So not ideal, but quite common, especially in rural or agricultural areas, out of choice, because there's one supply and only one way to get water into a community. So that's a branch, typically, or a tree layout. Branch, most common term. And there's some aesthetic issues around that too, because the further away from the supply you get, you end up with accumulated material that you've got to flush out. And it depends on the material. Here's a grid. And grid, basically, you can see, you still got the main trunk, but the ends of the distribution main are also looped. So now water can move in more than one direction. So water may take a left turn off the trunk main, but it actually can turn right and feed back in. And so now you have more than one feed and supply into an area. That will bolster the grade line. Operationally, works really well, because if you have to isolate a block, depending on where your valves are placed. And again, helps preserve the grade line. So greater water flow from a particular point in the system, at least two directions. You can see you've got multiple. Now that you've got these linked systems, if you had to isolate even a portion of the main of the trunk, water will bypass and move through the distribution mains into downstream portions of the system. So much more preferred. Shutdowns have a smaller effect and fewer dead ends, which then can create water quality issues, right? Here's the arterial loop. And the difference, you've still got the loops, but now you have larger, instead of in the smaller distribution mains, you have larger diameter mains off the main trunk, and that will allow for the greatest amount of energy to be preserved. So whereas the example before, the grid layout, these may all be 150, or in older systems may even be 100 millimeter lines. In North American context, if you go below 150 now, some cities now even a distribution main is 200. But for a lot of areas, there are still lines that are 50 millimeters in diameter. Well, thinking of the grade line now, that grade line is going to be steeper the smaller the diameter because velocities are going to be increased, right? So the arterial loop system allows for larger diameter mains looped, so you have multiple feeds into an area. So now, imagining the earlier slide with the grade line is much more robust because you could move a lot of water through multiple mains to the end point in the system. So that connecting up those plexiglass tubes and sending them vertically until the water runs out, you would see a much flatter grade line in an ideal situation where all the valves are open, right? If operators close the valves or forget to open them, or contractors close them, now an arterial loop becomes a tree. So as operators, again, I keep saying to operators how important their jobs are, because closing a couple of valves in this layout immediately defeats the idea of all that money that was spent on looping. And as an operator, you can figure that out pretty fast by looking at the pressure gauges. There was a situation in North Van where a contractor installed a subdivision and brought in 200 millimeter pipelines in a loop like this. But imagine in this corner, the top corner here, the contractor basically hit a large rock, and for the extent of one property, capped the water main and connected the two 8-inch mains with a 1-inch plastic line. So as long as all of the valves everywhere were open, pressure gauges wouldn't tell you a difference. But in a dynamic situation where there was a lot of flow and one valve got closed, all sorts of people in the subdivision were saying, we have no water. And it wasn't until we actually dug up that location that we found that the main wasn't connected at all. So that's a pretty extreme example, but it's used to illustrate the fact that if you are going to design this kind of a system to keep the energy, to preserve the dynamic head in the system, the valves better be open. And your engineers had better done the job correctly and size the pipe. If that's all 4-inch water main, 100 millimeter, probably not good enough. But based on current design standards, they build it accordingly. That is the system that's best going to preserve the energy, right? The most robust layout, right? It will meet, because of the larger diameter water mains, remember our flow Q equals A times V, the larger area, cross-sectional area, means velocities no longer have to speed up. So the flow will be good, and you can supply multiple directions to a single customer. So in that case, in this situation, even an emergency with a fire hydrant being turned on or multiple fire hydrants being turned on will preserve the grade line, so it's sufficient enough not to strand any of the customers that are at higher elevations. And that's one way of dealing with the loss of energy as water moves through a pipeline. And one of the questions on the exam, or a couple of them, will be about thrust. So water hammer is defined as basically a rapid change in velocity, a change of direction. So if you, as you know, if you slam a valve shut, all of that flow, especially in a water main break, right? People are, their adrenaline's pumping and they want to isolate the main so the damage is minimized. You've got high volumes of water at high velocity. And if you interrupt that flow, all that energy has to go somewhere. And it is basically a rebound effect. Throwing a ball with force against a wall, that ball will come back. And it will take multiple cycles to lower that energy. And if you've seen pressure gauge readings on a system where someone has shut a valve close, it can be up to 200% of the operating pressure in the system. Well, that will damage pipeline. And I was guilty of that once in North Van. We isolated a water main too quickly because of a break, and we split open an old cast iron pipe like a zipper, one full pipe length, so 4.5 meters of that old pipe. So we now have 2 repairs to do and a lot more damage. My superintendent was not very happy with me, but you know, you're in panic mode. This is, you know, in one of my early days as an operator, and we isolated the main too quickly. So hydrants or valves can be closed, open or shut too quickly. And of course, a pump may stop in a power failure or a failure of the pump and it shuts down without some proper control valve on the discharge side. And you get these huge swings, and it's both ways. So up over 100 PSI, say, goes to 180 PSI and then down to 30 and then slowly oscillates back to normal. The amount of damage that can do is tremendous. And of course, that's all the energy trying to find some place to go. So when we talk about pumps, we'll talk about surge relief, where a surge in energy can be absorbed and sent out to atmosphere or a splatter on the floor of the pump station before it can damage pipelines. But that's that energy being built up through high velocity and then suddenly stopping it. Not good. So water hammer is the rapid change in velocity that can create a pressure spike, right? So the pressure waves travel along the pipeline, they hit something, and it doesn't have to be a solid cap or closed valve. It could be a bend, and you can actually see the bend being pulled apart until that energy is dissipated. And all it takes is one pop, and now you have a water main break. As operators, we need to understand that and make sure that when we're operating a valve or a fire hydrant, we do it very slowly. And the temptation, especially if you're dealing in the middle of the night with a bad water main break and the resident's saying, my basement's flooded, shut it down quickly. And it's very hard to tell them, oh, we're shutting it down as quickly as we can. And the rule of thumb, basically, an old superintendent told me, was a minute per inch of diameter. So an 8-inch main, 8 minutes to shut it down? No. If the valve is operating, I've seen operators shut it down in 30 seconds. So you may not want to take 8 minutes to shut it down, but you do have to shut it down slowly. And otherwise, and you can hear it as you're shutting down a bad water main break, you will hear that velocity because you're slowly closing off the flow. All that energy is building up on the upstream side of the valve, and the whole ground will shake. It's kind of cool, although it can be very dangerous. So you have to make sure that by slowly closing the valve, it dissipates the energy before it can damage the pipeline or fittings or someone's plumbing and create more problems than the actual initial emergency. And it's the same with discharge systems. So when we talk about pumping, but a lot of the controls on the discharge, so the outlet side of a pump, are to make sure we don't change the energy, either increase it or decrease it suddenly. Water systems do not like sudden changes of energy that's available. So how we do that in the system, because if we've got to turn the water, a pipeline 45 or 90 degrees to go down the next block, we have to protect the water main. And there are lots of, I'll bring up some videos when we're doing the pipeline and pipe materials, because there are a lot of different types of joints in pipelines that are either push on, bell and spigot, or bolt together, flanged, or something in between like a mechanical fitting. They are designed in different applications. We like the bell and spigot in most of North America, or mechanical, because they're quick to put together in the field. But any change in energy and any change in direction can then change the grade line, increase head loss. And so we have to design them so that they can withstand the thrust. And there are tables for thrust at 100 PSI. If you put a 90-degree bend, you could take that 100 psi and increase it to 2000. Well, how do you cover for that? You either have to hold the joint together through what's called restraints, or you build a thrust block, which is really basically just a wad of concrete on the outside of the bend as a mass against the bank that will prevent that thrust. Because remember, when pressure is exerted in a pressurized system from elevation, from pressure head, that force will go equally in all directions. But if you turn the pipe, now we have unequal points where that pressure is exerted. And so we have to compensate for that. So there's an example of types of changes in direction, right? Could be the end of the line, like a T that's been plugged or capped. It could be a fire hydrant connection. And as soon as that fire hydrant starts flowing, you now have thrust back up against the water main, right? So, you know, whether that's here or here, but any change in direction to 45-degree bends or 22-degree bends, offsets, and this can work vertically as well as horizontally. 90-degree bend, we have to compensate for that opposite thrust. So there are tables that your engineers will create or get from pipe suppliers or from the American Water Works Association that show the size of the thrust block that needs to be built if you're going to use concrete, which is kind of the traditional way, bit of plastic wrap or timber, and then pour concrete. And it must come in contact with a solid undisturbed bank. And of course, it needs to set. You can't load it up while the concrete is still wet unless you physically restrain. So a joint restraint would actually be between the sections of pipe or the fittings, whereas the thrust block is, you know, basically built external to the pipe. Some utilities use both. We'll restrain the pipe for a certain amount of pipe lengths, which then creates the pipe itself becomes part of the thrust, and still build a concrete thrust block that cures, you know, 28 to 30 days later, that concrete sets up before it's at its hardest mass. So you can do both if you need to restrain instantly. And of course, I think more popular these days are the restraints that you can actually connect up between lug bolts or restrainer rings, that sort of thing. So here's an example. The top right photograph, a couple of valves with a cap, but these are mechanical, but they've got a physical restrainer ring that actually bites into the C900, the PVC pipe. So don't need concrete behind it because the pipe is actually held together so that it can't move. The picture below, you see a concrete thrust block. They use actually styrofoam in this case to help separate. You don't want concrete spilling, cement spilling all over the pipe. But they build the thrust block, and this is to stop thrust. This is a T, so the water is moving north-south from bottom to top and then turns left from right to left. And this thrust block is meant to compensate for the actual change in direction. And that will be quantifiable. It could be an extra 2,000 pounds that needs to be compensated. And the soil itself might have some factor, but the condition of the soil, if it's wet or very loose, needs more stabilization between the pipe and the bank. So the manufacturers create various types of restrainers. For instance, this little square here is on, it's called a bell joint restrainer, and it's a slip-on pipe. Not a very good picture, but it is a bell and spigot here. And these two follower rings, actually typical for PVC, hold it together. Some of the pipe manufacturers, the ductile iron pipe people, have different types of gaskets. So when you push the pipe together, the gasket has small metal chips in it, kind of like teeth. And so once it's pushed in, they cannot be pulled apart. So for earthquake protection. because you can have a pipe that doesn't crack like cast iron, but if it pulls apart when you have movement in the earth, then you still have to dig it up and repair it. So, but this is all based on how much energy in your system is available, and then how do you deal with the excess energy to ensure that it doesn't create a problem. So on the exam, might ask you about types of thrust blocks, typically that's concrete, or restrainers, which are typically mechanical add-ons that are put on at the time of construction. And they're all examples. So flange pipe joints, tieback or pipe joint restrainers, or so clamp restraints, or these actual mechanical restraints, restrained mechanical joints are typical. And depending, every city will specify what it's comfortable using based on the type of pipe it uses and based on the its experience and history and price and all of those things. But it's important for operators to understand that they are installed to equalize out the energy so that you don't have pipe movement based on that energy change, right? Someone closes a valve too quickly, or someone creates a demand through a fire hydrant. The pipe has to stay neutral and compensate for that excess energy. Now, how that works in terms of design and building a system, a lot of cities use water models to actually replicate how the system is working. So either in the summertime, the wintertime, high demand, low demand, if there's a fire, if there's a drought, and evaluate how the pressure holds up. And the model helps evaluate those emergency type situations. And including, so a city, say for instance, Victoria, that's 120 years old, some of the pipe goes back to the 1890s, so that's 130 years old, need to know which pipe to restore or replace or either rehabilitate in place or dig up, cut and cover, based on the best use to preserve the energy in the system. And how we calibrate them is typically operators in the field going out with pressure gauges and sometimes pitot gauges to actually flow the system and see, okay, is it performing like it's supposed to? Because if it isn't and your customers start complaining, it's a little late. Okay, so those are the concepts that we've covered today. I'm going to go through some review, and then I'll throw up the math answers from assignment number 1, and we'll be done for the day. Yeah, 15 minutes to go. Okay. So complaints of poor water quality most likely occur in what type of a water main layout? So the arterial loop, tree, grid, or nebular. Now remember, your exam's multiple choice as well. The tree system, right? That's the one that is only one-way supply with lots of dead ends. So this question is not about hydraulics, but about water quality. A main break may cause loss of pressure in the distribution system, which in turn may result in contamination of the system by, so the break may be caused by water hammer. We know it's not an increase in residual or ice. So the right answer is probably back siphonage, right? When water is pulled into the system that may contain contaminants. What is the recommended minimum water pressure in a distribution system, including fire flow? So we talked about that being the minimum. It's actually the arrow's in the wrong place. 140 kPa, 20 psi. I think that's just the slide. It's a little lopsided. 140 kPa minimum, including fire flow. Static, we want it to be higher, but remember, dynamic is when everything's flowing. What is the pressure at the bottom of a tank if the water level is 38.2 meters? So we're looking at this in kPa. We know it's about 10 to 1, 374 kPa, right? 9.8, right? We're going to talk more about water quality in the weeks to come. What water quality is most likely to occur at the end or dead ends of water mains? Taste and odor. Water may still be fairly clear because one of the issues at dead ends is there's not a lot of flow. So you don't get velocity, you don't get scouring, which can create the dirty water or the stained clothing. But it is perhaps a taste and odor problem. All right, pressure at the lowest point of a clear well is, I can't see it because of the, is 91 kPa. What is the total water depth of the clear well at its lowest point? Again, 9.2 meters, right? It's basically the 10-to-1 meters to kPa. Oops, he gave me the answer right on. What's the maximum water velocity through pipe under normal operating conditions? Anything over a meter per second is basically flushing. 7 meters, we've got a serious problem. So we're looking at 2.5 feet, 0.75 meters per second. These are normal operating conditions. When we're flushing, when we talk about flushing a water main, we do want it to be over a meter per second, because that creates the scouring that is necessary to remove sediment. What is static pressure head caused by? Well, it's not flow. Static means nothing's moving. Water pressure, well, it can't be itself. We're talking about the elevation of water in a vessel. And remember, it doesn't matter the shape of the vessel, it's the elevation that creates the static pressure head. Why are thrust blocks installed? Well, we don't care if water goes into a dead end, that's what we want. No, it's not to prevent leakage, because a concrete block is not a very effective way of sealing a pipe. What do you think? What's the best answer? To prevent joint separation. It's the best out of these four, right? To provide additional thrust to flowing water, it's partially correct, but sometimes a thrust block is the only thrust protection. So it basically prevents joints from separating when we have excess pressure due to a change in direction or pipe change, diameter change. Why should continuous positive pressure be maintained? Well, immediately we're talking about, actually there's too many little bullets here. The last one, to protect the system from the entrance of contaminants. It's not just the pipe wall that protects our customers from pathogenic contamination, but it's the pressure in the pipe. Then, as long as there's positive pressure, or the grade line is above our customers' outlets, then contaminants can't get in. What causes water hammer? Well, it's not the thrust blocks, it's not too many fire hydrants being used, but that's a potential issue there. The best answer is opening and closing valves too quickly. Filling reservoirs should be happening on a regular basis, and that should have been designed and taken into consideration. That's it. All right, so I'm going to bring up, just for the 2 minutes that we left, the math questions, and we're not going to go through them because at this point I'm going to do the review a little later, but these are the math questions for assignment 1. So I've asked Valerie and Ignatius to send them to you so you have them. That way you can take your time and look at them, because they're all based on the stuff we did in Unit 1. There's a couple of questions that are based on today, so if you didn't have those, you can calculate those now and work them backwards. But some of these are, this is the order of solving from bed mass. This is from the, what do we call it, the equation sheets they are given. And we're going to talk some more later in the program about totalizers, right? The average daily usage. So just remember, when you get a totalizer question on a math or on a test, totalizer is the readout. So it's not adding all 4 of these totals together, because the totalizer is basically a meter reading. So we took a meter reading on Monday. You notice all the times are the same, which is good. This is the reading, this is the reading. So we're looking at the difference, right? Subtracting the difference. And you can either subtract from the total from the last reading, Thursday to Monday, or you can subtract them from each other and add them together. But there's your answer there. Static water pressure, we've just done today. So if you had difficulty with that the first time, Bob's your uncle. Area of a circle, volumes, and then these last 3 questions are all volume questions. So these are the right answers. If you had difficulty with them, my suggestion is go back to the PowerPoint and work backwards now that you have the answers. But I'll ask Valerie to send these out to you. And that's basically it, guys. Guys and gals, ladies and gentlemen. Enjoy the rest of your week. I know your work days come to a rapid end, so we will see you. Actually, I won't be here next week, so Mike, yes, who's doing the treat, right, he'll cover off the disinfection piece next week.
Yes, so yes, thanks, Mike. Mike this morning told us that we're going to have a joint session. So those of you who are following today, the session for next week is going to start at 8 a.m. So we're going to send the links as soon as later this week. So you're going to be in for the 8 a.m. session next week, which will be the joint session. Thank you so much, Mike.
And we'll see you in 2 weeks at 3 p.m.
Yeah.
All right. Take care, everyone.
Okay. Bye.
Bye-bye.